Thank you. Okay, so I brought my laptop as backup also, since it has my notes on it. So yes, my name is Matt. I'm from YouTube, and I'm going to talk about super resolution at scale, of course. No, that's the laser part. There we go. So I don't think it's too hard to motivate what super resolution is or what we might be doing with it, but I'll try to be succinct. So at YouTube, we have a ton of user-generated content, and it spans 2 decades. This is of capture technology, varying production ability and effort, and about 20% of watch time still comes from videos that were uploaded at 720p or below. You know, we talk about 4K. We love 4K. We love 8K too, but. And in the literature, in the research, the problem of blind video super resolution is the problem of upscaling something that's low resolution to high resolution, where you don't know things like specific sensor noise, how blur happened, what compression artifacts might be there, just unknown. But to put a more positive spin on it, what we aimed to do with this project was to bring content up to par with what would have been possible if you were capturing something with modern technology. So I've divided this talk into 2 sections, and I'll try to be fast. In the first, we'll talk about model selection, training, and evaluation, and in the second, we'll talk about how we deployed it at scale. So this is actually, the previous talk was a very good lead-in to this one. Some wonderful slides, so we don't have to cover a ton of them. So in the beginning, we cast a very wide net. If we could get it to work, we would try it out. And the results consisted of 3 main architectures: convolutional neural networks, generative adversarial networks, and diffusion models. I've listed some of the pros and cons here, but to save time, I will just say, you know, diffusion models gave us the right trade-off of quality we would see, but with the downside that they are expensive. We will not. So the real question was, how did we work around that? I'll get to that later. So in model training, what we implemented was something, we took a few approaches. We implemented a diffusion model, as I said. We took a lot of cues from this paper called Redshift. It was, at the time, close to state of the art. It had a good loss function that incorporated both PSNR and LPIPs, which was mentioned in the previous slide, so perceptual metric. It was targeted at reducing diffusion steps, and typical, you know, when stable diffusion came out, I think the standard technology was run it for 1,000 steps, and you'd wait a long time. This one, we were able to get down to a handful. We basically ran studies to say, can you do it at 8 steps, 6 steps, 4 steps, and, you know, trade-off. It was also reasonably simple to implement. And get working, so that's always a positive when you've got a few people and limited time. The other main thing, so once we got it working, so we had a diffusion model working, again, based on the first paper, our main work shifted to improving it. And how do you improve ML models? You focus on the data. The main tool we had in our toolkit, and had continued to use, is from this paper called Real ESR GAN. Yes, it implements a GAN. And it follows, well, go into the next slide, a little bit more about it. So the Real ESR GAN method is really nice, and I want to tell you about it so that you can all pick it up if you need to. It simulates complex image distortions by applying multiple degradations sequentially, but also randomly. So it has a set of degradations it might do. Maybe you've got Gaussian blur with certain parameters. That's a very simple one. You have compression artifacts, you know, just throw it through FFmpeg at different CRFs. Let it pick some randomly, and it will do multiple passes. And you get out some really, really good before and after pairs, low quality and high quality pairs to train on. This is just one example. It does a pretty good job. So the next part of you have a model, that's great, but now you have to go evaluate it. So there's some standard metrics, PSNR, SSM, et cetera. But at YouTube, and this has been talked about maybe at this conference, but other conferences, we use something called UVQ for evaluating delivered quality. We did not use this as a metric for training the model. This is purely a metric for, what do we think our users really enjoy this content or not? It's a reference-free metric that gives a score between 1 and 5, basically a MOS score. And we saw significant improvement for lower resolution videos, especially, usually in a 0.2 to 0.3 range. And again, that's on a 1 to 5, so quite substantial in our metrics. Baseline was bicubic, and as you can imagine, or if you could just literally imagine, that's kind of blurry. And then smaller improvements as you got from 720p. I forgot to mention, for this algorithm, we were taking it up to 1080p. We weren't trying to push beyond that. Below 360, so content that was uploaded a long time ago, 240p, quite a bit of that was so low quality to begin with, it kind of struggled to bring it up to something. So there are bounds. There are good trade-offs here. One of the interesting things I would say was we saw places where our UVQ score outperformed, right? A human rater would actually give it a slightly lower one. The key thing for us was, well, two key things. One was it was directionally correct, and that helped. But also subjective evaluation. A little bit goes a long way, very powerful, very useful. You want to validate your end-to-end results, and that's always been good for us. Right, so, I think I'm in sync. We had something that worked on a single video, which was great. And product managers and other people in this room were saying, hey, could you just upscale this video? What does it look like on this video? We had a member on the team who said, someone hit my car, I have video of it, can you upscale it and maybe I can see their license plate? The answer was no, but I tried anyway. So you go from one video, but YouTube, over 20 years, has over 20 billion videos that have been uploaded. And so, like I said, we took a diffusion model, and it's expensive. So the question is, how do I deploy this at scale? What can we do? And really, this is the key from, we took a small team exploring a problem, but we're engineers, now we have to exploit what we have. This should not be you've seen graphs like this before. So first, we are very selective about which videos we apply this to. The power law is strong with how popular videos are on our platform. And we use this to our advantage. We are not looking at 20 billion videos. We can rank that many. Computer can take a number and sort. That's pretty easy. But we're trying to prune this down to a much smaller number, orders of magnitude smaller. The other thing is, so a lot of views are driven by only a few videos. So the first thing you do is find that subset of videos. Other selection criteria is what resolution was it uploaded at? Very trivial. But then the next one is, we're not doing this in real time. We can wait. There have been a lot of talks about ultra-low latency and live. This is the exact opposite end of the spectrum. This is content that might have been uploaded 10 years ago. It can wait. And it does. If you want it to wait a week, it can wait a week. So in essence, what's going on here is very simple. So it's hard work making a model, very easy to run a cron job. We are basically re-ranking videos once a day, picking which ones we want, and with the budget we have, process those. The other big thing here is that now we've picked a video budget. We have to make sure that we can squeeze the most juice out of that budget. And we have to do that with the help of two big pieces of infrastructure. And trust me, YouTube loves its infrastructure. The first is the video processing stack that YouTube uses to handle transcoding and more. Kirk mentioned the live infrastructure. There's more to it, let's just put it that way. And the other piece of infrastructure is the general base cloud computing platform. Because of our somewhat loose requirements, the video layer can use the cloud's opportunistic resources. All major providers have this now. They even have this for GPUs. And another thing we were able to take advantage of was multiple generations of TPU. because we were not latency sensitive, we're not trying to keep up with that 8K 120 FPS, which was an amazing talk. Also, the 4 generations of TPU, rule of thumb, each one is about twice as, the newest one is like twice as fast latency-wise as the previous one. So it's okay. We can smear these out. Some days we got 5x more capacity than others days. That's also something we didn't really mind. And so we're really targeting weekly, even bi-weekly throughput targets. On the minus side, using opportunistic resources tends to move toward more operational cost than CapEx. It's really nice to be able to say, to support these uploads, write this check, deploy this equipment. And then you just tune that to try to bring the numbers down. In this case, it's, we're only getting that 1x, not that 5x. I wonder if something's wrong. And anytime you start wondering, you're spending time, human time, trying to investigate something. The most important thing there, though, was this gave us a way to launch at scale without a big upfront investment. We basically had 2 full-time engineers working on this, and then we'd pull in 1, 2 other types of people as needed as we went through this. The last thing I want to say about this slide is, when looking at efficient infrastructure, we were really taking advantage of the temporal flexibility, and that's standard diurnal patterns of load and stuff. We'll fill the troughs naturally. But also spatial flexibility. We can push it around the globe sometimes. Usually it's mostly around the continent, depending on where the data is. So there's more detail to this. See me offline if you want to learn more. I don't think I can get this to play. No, so let's just skip over. Again, see me offline. And I really just want to wrap up by saying this had a tangible impact. So videos with super resolution enabled achieved about an average 1% increase in watch time on living room TV screens compared to videos without it. And we did some ablations to say, well, is it just the higher resolution, et cetera? But this was a pretty stable result. So pretty happy. And I will wrap up just by saying, future work, what are we doing? Well, number 1, make it more efficient. But like I said, we went kind of with the budget we had. We got something that was working. We're happy. We built out some pipeline. We're investigating 4K. There are different, I would say, product challenges there. HDR is a very interesting thing. Again, different product challenges there. There's lots of ideas in the literature on diffusion optimizations and fine-tuning and potentially fine-tuning of video generation models. And also finding, I mentioned data before, finding more real-world degradations that we've already seen some good work with a collaborative team that works on photos in that space. I'll wrap up by saying thank you, trying to get you back on time. And there's some before and after examples. I'll leave one of those up there.
Thank you very much, Matthew. Thank you. And like me, please save your questions for the coffee break, but I have a number of questions to you. Our next